welcome to our webinar series. Today's topic will be the STA, the Simultaneous Thermal Analysis, a short overview about the technique. As long as we are waiting, you will see a presentation. I'll explain to you about our instruments, about our company history, and some applications. During the talk, you all will be muted. Afterwards, we have a short discussion. If you have questions, please use the question and answer section or use the chat. In the last webinars, we had some issues with the platform, so it was disabled, unfortunately. In case you were already there, just drop us a mail if you have questions, if you have anything to say. Meanwhile, the chat should be working. So if you have questions and if you want to discuss after the presentation, please type it in there. We will answer it after the presentation. So okay, meanwhile, everybody should be here, and some people try to join but not do it so far. It's a pity, but as there are no requests pending, I think we can start here. So again, welcome to the webinar. Just a few informations. We will have a short discussion afterwards. If you have questions, type them into the chat, please. The webinar will be recorded. In case you missed something due to sound issues or video issues, you can request a video recording of the talk afterwards. First of all, I want to introduce myself. My name is Sebastian Seibt. I'm head of laboratory here at Linzais in Germany. I'm a chemist and I'm working for the Linzais company since 2013. I'm speaking German and English, and you can reach me via the mail address you can see here or via social media, of course. In case you have questions regarding customization of instruments, application issues, or you want to order a measurement, I'm the right person to ask for. And otherwise you can also contact us at lab@linzais.de as well. Also, I want to introduce the company. So some of you might not know the company yet. So Linzais was founded in 1957 by Dr. Maximilian Linzais here in Seibt in Bavaria in Germany, where we are still located. Dr. Maximilian Linzais was a physicist. Is the guy on the top left picture here. He was working for the porcelain industries or for machine manufacture of the porcelain industries that was located in Seibt. And he was one of the inventors of the classical pushrod dilatometer. Out of this, he founded his own business. And one of the first products we started with were these data loggers you can see on the bottom picture here, because in that times the computer was not that present everywhere. So the data that a device recorded had to be recorded somehow in an analog way. So therefore they invented these XYZ plotters as well. And this was one of the first big products that was sold globally. After the 1970s and 80s, the computer was available. These data loggers were no longer needed, and therefore we switched our key business from data loggers to thermal analysis only. In the meantime, the son of our founder, Mr. Klaus Linzais, was in charge of the company. So nowadays he's our owner, and his two sons, the third generation, Mr. Florian Linzais and Dr. Vincent Linzais, you can see in the top right pictures, they are our CEOs doing marketing and sales mainly, which is Florian Linzais, and doing the development and research, which is Vincent Linzais mainly. So this is how we are structured, and as said, we are a family-owned company, roughly 150 employees. 100 of them are in our headquarters here, and all the others work in our 3 other locations. We have one in the United States, where we have a lab, a sales office, and the service office. The same in China. We have a lab there. We have technicians there for repair and maintenance, and also, of course, the sales office. And in India, we also started a company now where we have a sales and maintenance office now. So this is how we are structured. And in all of the other countries, we have distributors, so you can reach us more or less in every corner of the world. As I mentioned, our main business area is the manufacturing of thermal analysis equipment, as well as for thermal conductivity and thermoelectrics. And of course, we also offer service measurements and test measurements in our labs worldwide. Coming back to our today's topic, this slide shows our product portfolio, and the upper line, the upper row, is the classical thermal analysis, which means differential scanning calorimetry, thermogravimetry in many ways, so thermobalances and DSC instruments, and of course the combination, which I will show you today, so the so-called simultaneous thermal analyzer, which is a combination of a DSC that measures heat flow and enthalpy and a thermobalance that measures the mass change. Besides that, of course, we have many different dilatometers for thermal expansion and volumetric expansion measurements and thermomechanical analyzers, and this completes the classical thermal analysis portfolio. On the lower line, you can see the instruments for thermal conductivity measurements, which is laser flash, heat flow meters, guarded heat flow or guarded hot plate instruments, hot wire instruments, many more. So a broad range for thermal conductivity. The same for thermoelectrics. We have a broad range of thermoelectric analyzers for measuring Seebeck coefficient, Hall coefficient, thermal conductivity, and electrical conductivity in combination. And of course, resistivity as well as conductivity. And the whole thing also for thin films, microchips, coatings, and that's the complete range we do. And for all these instruments, we do a lot of customization. We do high pressure variants, we do high temperature, low temperature variants, which makes it a little bit unique on the market. So that's our product range. Now coming back to our today's main topic, so the overview about simultaneous thermal analysis. As I mentioned before, the simultaneous thermal analysis means a combination of dynamic differential calorimetry and thermogravimetry. So you have a thermobalance that is equipped with an EC sensor head, more or less. This schematic drawing here shows how the typical setup looks like. So here you can see a thermal analyzer containing a thermobalance unit in this lower part. So you have an in-house manufactured balance cell that is a beamline balance in a monolithic block out of aluminum or out of stainless steel, typically. And this beamline here is fixed in one angle point in the middle. On one side, you have a physical counterweight. On the other side, you have a connector pin where a sensor rod is connected to. The complete beamline is monitored by infrared and light diodes, so the exact position of the balance beam is recorded quite constantly and in a very narrow range. And once the mass of your sample on top of your sensor rod changes, this beam would go up or downwards. This movement would be recorded by this light diodes more or less, and there is an electric magnet connected to this beamline, and this magnet can compensate the movement. So either by lifting or lowering this beamline, you can compensate the movement caused by the mass change of your sample. This compensational voltage the magnet needs is your weight signal that the balance can more or less investigate or can record. And it's a quite proved and well-developed concept. And you get a resolution of some micrograms, maybe some nanograms. The yellow part is the sensor head. As said, these are plug-and-play sensors. You can plug them in here. When the furnace lifts up and the furnace is open, from the top side you can insert a rod. And on top of the rod there is a sample holder consisting usually of a sample and reference crucible within a platinum or metal bracket or sensor head. And this is the typical DEC sensor. So the DEC information, the DEC signal is obtained at the sensor head, and the weight change signal is obtained out of the electric magnet down here. So that's what the instrument measures. The blue part up here is insulation material, and the red part you can see next to the insulation is the heater that surrounds the inner sample chamber. The configuration here has an open furnace, so the gas exhaust is on top, but you also have the same setup with the gas exhaust at the flange down here. So either you have a gas flow coming from the sample gas in here into the furnace, going out at top, or it gets in here and gets out at the flange directly. There's another gas inlet. So you have a purge gas access, so the sample chamber, the balance chamber can be purged with inert gas usually, and the complete inner chamber, so balance unit and sample unit, can be, of course, evacuated. The gas control is achieved by so-called mass flow controllers, so we have automatic gas control that can be controlled by software. And if you have an open furnace, the outgas or the exhaust can be connected to evolved gas analysis. That means you can couple a mass spec or infrared spectrometer to get more information about the outgassings, of course, time dependent or temperature dependent. And that's the general setup, how our balance or STA looks like. The resulting signal that is typically recorded looks like this. So that example shows the composition of a gypsum sample, and what you can see is the orange curve here is the temperature dependent mass change of the sample, and you see at a certain temperature, somewhere between 100 and 200 centigrades, there's a two-step mass loss, which is the loss of water here in that case, and you see it's a two-step mass loss curve. This is typically what a TGA shows. So you can get an information about how much mass is lost, what's the content, so what's the humidity or water content of the sample, and of course other decomposition reactions I will show you later. And simultaneously you get the green curve here, and the green curve is the heat flow. So you see there are some peaks, which means at that point when the mass loss takes place, there is some heat flow change. So there is an exothermic or endothermic effect going on. Direction defines if it's endothermic or exothermic. And if you integrate the area beyond the peak, you also get a readout about how much energy is released, or in that case, how much energy is consumed. In the further curve, or here at higher temperature, you see there is some additional effect, and even there's another one. And these are effects that more or less do not show a mass change. So the simultaneous signal of the mass stays constant. So out of this, you know that these must be phase transitions melting. In that case here, it's a quartz transition up here at around 575 centigrade. So that's the quartz transition. And this is also a phase change within the material. And you know that because there's no mass change. So phase transitions from liquid to solid or whatever, or from one phase into another phase, usually do not show a simultaneous mass change. A decomposition reaction, however, does show that. And that's how you can identify effects and how you can get information out of your sample run. And of course, the advantage of doing this simultaneously is you do only one experiment. It's exactly the same sample where you get heat flow and mass change, and it's cost effective, of course, and space saving if you do both in one instrument. So that's a typical STA experiment. As the title of our today's webinar already suggests, this is an overview. This is just showing you what we can do, what we have, and what different versions are available. So I want to introduce a little bit our STA program to you. And at the top center, you see the so-called STA PT1600 version, which I would consider as our base unit. This is a very modular setup. You have a platform, you have a furnace lift, and you have a furnace holder where you can put any kind of furnace on top. So the temperature range and the atmospheric range depends on the furnace you select, which is, as said, modular. And this platform can do more or less any condition we offer. On the left side, there is the lower edge. So that's the STA PT1000. And as the name suggests, it goes up to 1000 centigrade. However, here you do not have a flexible, modular, exchangeable furnace. Here you have an integrated furnace. It's always the same furnace that goes up to 1000 centigrade. So it's for a very specific experiment, and it's for the lower temperature range. It's a little bit faster due to the lower thermal mass. However, the possibilities and options are restricted. On the right side, on the top line, you see a very specific instrument, the so-called magnetic suspension balance, which is a contact-free sample chamber. That means the sensor head is not connected by a rod to the balance unit. In that case, there is a magnetic coupling. So you have two magnets that keep the sample holder in an elevated state all the time. And there's a magnetic coupling. So you have an enclosed furnace with a very defined volume. And this is designed for very corrosive atmospheres, for very reactive samples, for very critical conditions. And it's a very special version. On the lower line, you see two other special versions, or one other special version, and that's the so-called pressure balance. We have a floor-mounted STA high pressure 1 and 2 system. 1 and 2 defines the configuration of the pressure vessel because we have lower and higher pressure rates. You can go up to 150 bar. And we have also a tabletop mounted system, which is again up to 1000 centigrades. And this is our pressure version. So this is our complete STA range that we can offer. And depending on the customer needs, we can configure a fitting system or fitting solution to the application that the customer is looking for. The following slides are about our general design and about all the options that you have. So our measurement setup in general is always a vertical setup. I have to state that there are two possible ways of setting a thermobalance and creating a STA unit. So you can do it either horizontal or you can do it vertical. And if you do it vertical, you can do it hanging with the sensor head on hanging from a unit downwards, or you can create it standing. So the balance at the bottom side, the sensor head upwards. First of all, in the very far past, in the very distant past, we had a horizontal system, which is good for balance, but for DEC it becomes very difficult because you need two separate rods holding two crucibles, and you have a lot of disadvantages because of the sensor exchanges, the handling, the gas pathways, and the problems due to expansion behavior of these rods. So that's why we stepped away from the horizontal setup. Nowadays, we have a vertical hanging and standing system. Our standard design is a vertical standing design, so that's the design you already showed on the first slide. The advantages, of course, easy sample handling for the customer, easy sensor exchange. It's just plug and play. It's a stable position for the sample. It's a rather complex setup, but it's the one configuration that you will find always at the market, and most competitors do it in the same way. For doing TGA and DEC in combination, it's the best fitting setup. However, we also offer a hanging balance in case of a balance. If you just need the TG signal, a hanging setup has the big advantage that a hanging balance unit always hangs to the center of the Earth due to gravity. So it's almost every time in the exact best possible position. And it's the best possible TG signal you can get. However, the sensor exchange and the DEC setup is a little bit complex. If it's the TG only, we also offer vertical hanging system for TG only because it gives you a little bit extra advantage regarding the TG signal. But for STA, we would prefer a vertical standing design. In the hanging system, you also have a little bit dangerous gas flow path, so you could blow out your sample. That's also the reason why we prefer the standing design. But as said, our STA is usually the vertical standing one. Our TGA can be hanging or standing design depending on the application, and that's why we do it in the way we do it. And that's what, by the way, most competitors do in the same way. We offer, as I already mentioned, several options, which means we offer sample robots for all of our balances and STA units. Of course, we offer different vacuum pumps. For ultra high vacuum, we have turbomolecular pumps that can be coupled to the system and attached to the system. For lower vacuum levels, we have membrane pumps or variety that fit to all of these systems. We offer vapor and humidity generators in case of humidity or coal gasification experiments. We have different gas dosing systems, of course, individual gas dosing systems, depending on what exactly you want to do. If you want to have a very complex gas control or complex gas setup, we have external gas control boards, and we can also add gas analyzers for the outgassings and for the exhaust. As I mentioned before, we can couple infrared spectrometers, mass spectrometers, and even GCMS mass spectrometers for characterization of the decomposition products to get even more information about whatever you decompose in there. Regarding the furnace, our STA can operate from liquid nitrogen temperatures, roughly minus 150 centigrades at the sample, up to 2400 centigrades using a graphite or tungsten furnace. You can add almost any of these furnaces to our systems, depending on the temperature range you want to run and depending on the atmosphere you need. There are different possible options. The standard option would be a SiC heated furnace, which is cheap and which is quite robust, which allows almost any kind of atmosphere. However, if you want to have faster heating and cooling, we have metal furnaces. We have even infrared furnaces. We have metal furnaces for platinum rhodium heating and even tungsten heating for higher temperature range that are quite expensive. However, have unsurpassed speed regarding heating and cooling rates. So it depends a little bit on budget, availability, and it depends a little bit on the temperature range, as well as desired atmosphere, which furnace might be the right one for you. We have also special furnaces. I only listed 2 of them here. We have them on demand. We have vapor furnaces. As I mentioned, we can couple water vapor units to get experiments done in humidity. And we add as well as infrared furnaces and high-speed furnaces where you can reach really very fast heating and cooling speeds up to 100 centimeters per second. And that's just 2 of them. So they are available on request, but they are for very special applications, for very special custom designs. So that's the furnace program we offer. And not only the furnace is a very flexible optional part, but also the sensors. Speaking about the TG-DSC combination, we have the typical standard DSC sensor head, a so-called DSC heat flux sensor, which is basically a ceramic rod with a ceramic disc containing a metal sensor head, which has space for 2 crucibles. These crucibles are made out of aluminum oxide, made out of aluminum, gold, platinum, quartz, sapphire, graphite, whatever you need. Again, the crucible material depends on what kind of sample you want to measure and what temperature range you have. They are available out of all these materials I just mentioned, and they all fit into the standard DSC head. If you want to run bigger sample amounts, we also have a so-called 3D DSC sensor, which allows the use of bigger amounts. It does not follow any ASTM anymore. However, it allows you to run up to 1 milliliter sample volume. It requires a little bit complex calibration, but it works. And in case if you have a very inhomogeneous sample, it sometimes has the advantage that it's a little bit higher resolution than the classical 0.12 milliliter standard DSC heat flux sensor head. Of course, you can also run the TG-DSC instrument as a TG only or as a DSC only. If you want to run it as a DSC, of course, you need a DSC sensor. However, if you want to run it as a TGA, you can exchange the sensor head and use a TG only sensor. We have TG-DTA sensors as well, which is a sensor that cannot quantify the heat flow as you measure the heat flow just in one point and not with this clamp or this sensor head out of metal where you measure the complete heat flow environment of a crucible. In contrast to that, the DTA sensor here has only 2 spot thermocouples that measure the temperature at each crucible at one point, allowing you to measure at least if something is exothermic and endothermic and at what temperature something happens. However, the TG-DTA has the advantage that you can also measure bigger sample volumes of 0.3 milliliters, and you can measure in more corrosive atmospheres, or you can measure corrosive samples as your sample holder does not show any open blank wire or thermocouple that could be corroded anymore. While the DSC sensor with its naked metal surface sometimes tends to react or tends to be corroded, the DTA, the drawback is the DTA does not provide a quantitative analysis, but a qualitative analysis of the heat flow, and there's no risk of breaking the sensor. So we have the DTA sensor, and we have the pure TG setup. For the pure TGA, we have a sensor rod out of ceramics with a flat top or with a little pin. It depends what you prefer. And then we have flat crucibles of custom volume up to 12 milliliters, and we have pinned crucible of custom volume up to 12 milliliters that can be attached to the TG only sensor. All these crucibles can be made out of any material, usually different ceramics or different metals. They are also available as a meshed crucible type if you want to have a gas path through the sample for measuring sorption, measuring high reactive samples. And we also have very customized solutions again, like a hang down system where you can hang in some foils or hang samples into a gas flow. So this is the range regarding sensors and crucibles. And again, this is a very flexible system. So what's important for you to know, if you ask for STA instrument, first questions we would ask would be what kind of temperature range, what kind of atmosphere do you want to run it, and what kind of samples do you have? How big is the sample? Is it homogeneous or not? How reactive is it? And out of this, we can configure the ideal configuration for you. The next slide just shows some typical applications to make clear what we use the instruments for. So beginning with pretty easy experiments like oxidation. So one of the typical uses of rather the TGA is the oxidation and the aging. So slow mass increase over time. If you have oxygen or oxygen containing atmosphere, how fast does the mass change and when does the mass change? And there's the DEC experiment, the so-called oxidation induction time. In that case, you measure the heat flow signal, you start it in an atmosphere, bring the sample to a certain temperature, then you switch to oxygen, and then you measure the time, how fast you get a response signal showing you the heat flow change of the beginning oxidation. And the oxidation induction time in combination with the mass change of just a sample in oxygen atmosphere gives you a pretty good prediction of lifetime, prediction of aging, and that's frequently used for polymers, for oils, organics in general, fats, and whatever. Another application would be the analysis of composition of multi-component system like water content, volatile content, carbon dioxide outgassings, ash content, melting and decomposition, and so on. So you can get a good information about composition. And of course, as I just mentioned, you can get good information about the grade of humidity and volatiles by just looking at the mass change. Besides that, we have the typical DSC applications, which is melting and boiling point analysis for multiple industries. We have phase changes like crystallinity of polymers, pharmaceuticals, and even metals, alloys, and construction materials. And that's what phase changes are all about. So melting and evaporation is just one of it, but you can also have information about glass transitions, information about structural changes from soft to hard, from hard to soft, stuff like that. That's a typical DSC application, and that's used in many, many industries. You can measure the general influence of atmospheres on materials, like I just mentioned, if you have inert atmosphere versus oxygen-containing atmosphere. And fuel cells is just one example, but you can measure that and apply that on any industries as well. Something that's very interesting for a TGDSC as well as the sorption. Of course, a TGA shows sorption in regarding the mass change. So you can do gravimetric sorption. You put a sample in, you apply a certain gas, the mass changes by gas uptake. So that's where sorption is usually recorded. You can do it volumetric, but with our instruments, mainly you do it gravimetric, like storage capacities of hydrogen storage materials and stuff like that. And in case of TGDSC, you can also get information about the heat of sorption. So how much energy is released or consumed during absorption and desorption. Heat of fusion I just mentioned, but we can also investigate, of course, real reactions. So the DSC does also provide the possibility to measure reactive enthalpies, like how much energy do you get if you burn something off, how much energy is available out of a different, at a certain point, out of a decomposition, out of a reaction with an atmosphere, reaction with another compound. That's what you can do with a STA in general. At the very end, I have some application examples so that you have a little overview how that looks like. So this example is a pretty simple one. It's a decomposition of rubber. There was a rubber sample that was heated up first in inert atmosphere, in nitrogen atmosphere, and it shows you the decomposition. Again, the orange curve shows you the mass loss or the mass change. The green curve shows the corresponding heat flow signal. What was done here was the sample was heated to the first isothermal segment, roughly at 300 centigrades. During heating and during this plateau, there was a slight mass change, a slow mass change ongoing until reaching a plateau, a stable mass again. There was almost no DSC signal. So you can be sure that this mass change is surface volatile, surface water that just evaporate without causing a bit heat flow change. Then the sample was heated up to roughly 700 centigrades. During that heating segment, there was a huge mass change and there was a simultaneous huge reaction peak, which symbolizes the pyrolysis of this rubber sample. And finally, the atmosphere at this point was changed or was switched from nitrogen to oxygen, and then the heating was again performed up to 1000 centigrades. And this third heating segment in oxygen shows a very, very rapid mass loss and a very big peak again on the DSC curve. And this is the burn off. So this is the burn off of the organics you formed during pyrolysis in the second decomposition segment here. Out of this experiment, you can read out the mass change steps. You can read out the enthalpy of this decomposition effect. That gives you an information about how much volatiles you have, how much humidity you have, how much carbon content you have, how much residual mass, so inorganics and fillers you have. And out of this, you can have a pretty good idea how your sample was composed, more or less. The next example is the decomposition of calcium oxalate, which we use as a more or less reference material for our STAs. In this case, a mass spec was coupled, so we also monitored the mass, by mass spec, the mass of water, the mass of carbon monoxide and of carbon dioxide to show you what comes out here. Again, the orange curve shows you 3 mass loss steps, shows you the mass loss. The green curve is the DEC signal, and the brown curves here are the masses of different AMU lines, especially of water, carbon monoxide, carbon dioxide. In this case, the heating was performed linearly, so the sample was just heated, and what you see is a first mass loss at roughly 200 degrees, which is the loss of water, and this water loss is going hand in hand with an endothermic effect. This effect is the decomposition. As said, it's well known, it's the loss of water. You see the ion current of carbon monoxide and carbon dioxide do not show any effect. However, the ion current of water goes up, and that means water is released. The mass spec records some water that is released here. There's another little peak on the water line over here, which means there is maybe some water coming out here and going slower to the mass spec. In at higher temperature, it goes off. And as said, the first decomposition step is the loss of water. Then you have a second step, which you can see here shows a big effect on the carbon monoxide line, so that you can be sure this is the release of carbon monoxide. Again, you have a mass change step, you have an endothermic effect on the DEC, and you have a huge signal on the carbon monoxide line and a rather small signal on carbon dioxide line here. And then finally, you have a third step, roughly at 700 centigrades, which is the loss of carbon dioxide. You see carbon dioxide mass signal goes up here. Carbon monoxide shows almost no effect, and water shows also no effect. And out of this, so coupling a mass spec, you can get a pretty good information what exactly is happening. And as said, the decomposition of carbon oxalate is well known, and we use it as a kind of reference material to check if the TG, if the DEC lines and curves fit to the literature values, and if everything is fine with the instrument. Besides that, as I mentioned at the very beginning, we have also very special instrument, very customized instruments, and we can couple inductive heaters, infrared furnaces. We can separate the electronics if you want to place your analyzer in a hot cell, in a glove box, in toxic atmospheres. We can separate anything, so you have a naked thermobalance, and you can have the electronics and control panels all outside of a hot cell, outside of the glove box, to have some user safety, and that's also possible. And we provide generators for water vapor, for humidity, and of course we can do sophisticated gas control like you see in the top picture with an extra gas control panel that's coupled to the instrument. And in that case, it's a pressure instrument, so you also have a pressure reducing setup with condensational trap and so on. And that's what we can do as well. And also for this special configurations, I have some slides in here, and this shows you multiple curves in one diagram. This is the hydrogen absorption on the titanium surface. So at 700 centigrades, hydrogen was applied on a titanium sample at different pressure levels, starting at a low pressure. At a very low pressure, hydrogen was added, and once the signal was stabilized, the mass change was recorded. Then the pressure was increased a little bit. The experiment was done again. It was repeated with ongoing pressure increasement. And finally, the result shows you absorption curve for hydrogen on this titanium surface at 700 centigrades. This curve shows you that from 0.5 bars and onwards, the amount of hydrogen, the mass of hydrogen that can be sorbed by this surface was no longer increasing. That means the saturation level is roughly at 0.5 bar. And even if you go up to 5, 6, 7, 8, 10 bar, the saturation level is already reached. And out of this, you can investigate the sorption behavior of substances, of catalysts, of storage structures, whatever, metalloorganic frameworks or whatever you have. And as you see, these experiments are what is usually done with our pressurized systems, with our special configured systems. This weird graphics is how it looks like if you do an experiment and you record not only 1 or 2 traces with the mass spec, but this is if you track multiple gases by mass spec. So you have multiple gas lines on the lower part of the diagram. You see a lot of different peaks. This is different gas types. So you see SO2, CO2, water, different carbohydrates and hydrocarbons. And this is how you usually investigate unknown samples that compose or decompose in multiple different steps. So this was a cement sample releasing carbon monoxide, carbon dioxide, some sulfur components, some volatiles, and shows you a quite weird yellow mass change curve, and also very much and multiple effects on this red DST curve. So this is a real experiment where you see a mass change can really increase or improve the experiment by telling you what exactly is lost at each segment and at each effect, and what exactly is going on by identifying the outgassings. So far about what the instrument does. Now we come to my favorite part, because in this webinar, and those who joined us on Tuesday already, they already know it. In this webinar on Tuesday and today, I'm very proud that I can announce that we have, in the last 2 or 3 years, we have created a completely new instrument design. And beginning in April, we will launch our new instrument design, beginning with the STA instruments. That's why I also do this talk again. And this, what you see on this picture here, will be the future of our STA analyzers. We have a completely new design with upgraded housings, upgraded touch panels, and some improvements on the instrument. They will be all in the new brochure, and we will present it on the Analytica conference in Munich right in April. We started with the STA and also with, of course, DSC and TGA instruments, but all of the other instruments will follow shortly. The new design comes with a complete new software package with a lot of user-friendly new features. Some of them I already can mention is we have a much more functional touch panel where you can control much more options directly at the instrument. We have an integrated toolkit panel, so a lot of stuff that you need for operating the instrument is already integrated there. We have improved furnace lift that has lower and noise level, lower vibration level. We have a completely new software package. We have new sensors for plug and play features, so the system will automatically recognize the configuration. That means it recognizes what kind of thermocouple you have, what type of sensor you have, what kind of furnace you have. So it tries to be as user-friendly as possible. And also the design looks a little bit more modern. As said, the planned launch or the launch will be in April 2024. And for those who are very curious, you can visit us at the Analytica conference in Munich in the second week of April, as far as I know. And then you can have a live demo of the new design and new features. That's the end of my today's talk. I hope you enjoyed it, and I have to thank you for your attention and thank you for your time spending with me.